The universe is expanding, and not just expanding, but accelerating in its expansion. This discovery shocked the scientific world in the late 1990s. Two independent teams of astronomers studying distant supernovae found that galaxies weren't just drifting apart. They were speeding up. Some unknown energy, was pushing the universe apart at an ever-increasing rate. We named it dark energy, and today, we believe it makes up 68% of everything. That's more than stars, planets, gas, dust, and even dark matter combined. But what is dark energy? That's the mystery. One of the first ideas to explain it comes from quantum field theory, the idea that even empty space isn't truly empty. According to quantum physics, the vacuum is filled with fluctuating energy. Virtual particles pop into and out of existence constantly, borrowing energy from the vacuum and disappearing again in mere fractions of a second. This restless sea of quantum activity gives space itself an energy, a kind of vacuum energy density. It sounds like the perfect candidate for dark energy. But there's a problem. When physicists try to calculate how much energy this vacuum should have, they get an answer that is 120 orders of magnitude larger than what we actually observe. This discrepancy is mind-boggling. It's been called the largest mismatch between theory and observation in all of science. To put it into perspective, if theory says the vacuum should weigh as much as a skyscraper, observations say it weighs less than a grain of sand. This gap highlights a profound ignorance in our understanding of the universe's most dominant component. So scientists have explored alternative ideas. One such idea is quintessence, a hypothetical form of energy that isn't constant but dynamic. Instead of a fixed energy permeating space, quintessence is imagined as a scalar field that changes over time and location. This offers more flexibility. It can vary in density, interact with other fields, and even influence the ultimate fate of the universe. But it comes at a cost: complexity. Introducing quintessence means adding an entirely new field to physics, one that hasn't been observed or confirmed. And it must be finely tuned to match what we see in cosmic data. Still, it opens a fascinating possibility. Perhaps dark energy evolves with the universe. Perhaps it was different in the past and will be different in the future. Another radical idea is that Einstein's theory of general relativity, while incredibly successful, might not be the full story. General relativity describes how mass and energy curve space-time, creating gravity. It has passed every test we've thrown at it, from Mercury's orbit to black hole imaging. But what if, on the largest cosmic scales, gravity behaves differently? Some scientists propose modified gravity theories, extensions to general relativity, that could account for accelerated expansion without dark energy. These include FR gravity, massive gravity, and other models where gravity weakens or strengthens depending on scale. These ideas are bold. If true, they could revolutionize physics. But they also face a challenge. Any modification must fit the precision measurements we have of gravitational behavior on solar system and galactic scales, which are already incredibly accurate. So far, none of these theories have been able to completely replace the need for dark energy. Another puzzle comes from the cosmic microwave background, CMB. The subtle patterns of temperature fluctuations in the CMB match cosmological models that include dark energy. Without it, the models fail to reproduce the observed structure of the early universe. This reinforces the idea that dark energy is not just an artifact, it's real, but its identity remains elusive. Some even suggest dark energy could be a hint of something deeper and more exotic, a new force, a hidden dimension, or even a multiverse connection. Maybe what we perceive as dark energy is the influence of parallel universes bleeding into our own. These are speculative ideas, but they're being explored because dark energy demands it. We can't ignore it. It affects everything. It shapes the large-scale structure of the universe. It determines whether the cosmos will expand forever, slow down, or rip itself apart in a final catastrophe known as the Big Rip. And yet, it remains invisible, undetectable by traditional means. We only know it's there by watching how it moves galaxies. This is why telescopes like the James Webb Space Telescope, the upcoming Euclid mission, and ground-based surveys like the Vera Rubin Observatory are so important. They will map the positions and velocities of galaxies across billions of light years, helping us understand how the expansion of the universe has changed over time, and hopefully, what dark energy really is. Until then, we live in a universe ruled by a force we cannot explain. It surrounds us, it guides the fate of galaxies, and it dominates reality. We call it dark energy, but it might as well be called the unknown.